Ship structures must survive harsh loading environments. Fabricated of high-strength steel, they are designed to be both strong and producible, with uniformly spaced internal substructure. Our goal is to analyze ship hull to all possible failure modes, to all load cases, to ensure required safety for each, and to optimize, size concurrently, all of the plate thicknesses, frame and stiffener heights, spacings, and cross-sectional shape dimensions in order to achieve the lightest weight and most efficient structure. Our goal also includes updating the CAD drawings with sizing data and the finite element model used for analysis. In Hypersizer, updated FEM properties for structural members are displayed with color. A section of the ship hull shows uniformly spaced internal substructure of transverse frames and longitudinal stiffened panels. Two notional designs are depicted. One is a sandwich panel that stiffens the outer mold line plating. The other uses longitudinal stiffeners to provide the required hull plating support. In Hypersizer, you have the option to select as many panel concepts as you choose to be considered in the optimization. Without changing the mesh, all of the panel cross-sectional dimensions and plate thicknesses are optimized to the loads from the ship FEM. Hypersizer will determine the lightest possible design for each selected panel concept and report their optimum design dimensions. In this way, the best structural design for all locations of the ship hull can be established. Steel is the material used today, but if your interests include polymer composite materials such as carbon graphite or fiberglass fiber with vinyl ester resin, then material selection and layup are also variables that can be traded simultaneously with panel dimensions. Hypersizer supports the different finite element modeling techniques of stiffened panels. The four most common are represented here. Techniques 2, 3, and 4 use beam and shell elements to discretely model stiffeners. Technique 1, which smears the stiffeners into the planar shell mesh, is most commonly used for ship structures. Technique 1 has many modeling efficiency and structural optimization benefits. All of the possible cross-sectional shape and size dimensions are available for optimization. Techniques 2 and 3 are limited in some of the important shape sizing variables, and Technique 4 is restricted only to sizing of plate thickness or composite laminate layup. Compared here are the individual panel object loads, extracted from discrete FEM mesh. All four methods give accurate results for axial and longitudinal bending moments. When in-plane shear forces are also applied, techniques 1 and 4 prove to be the most accurate, but all are still accurate enough. Regardless of which modeling technique is used, Hypersizer extracts loads from the FEA solution consistently and accurately. Once object loads are established, they are used for the exact same Hypersizer analysis methods, including strength, local buckling, and crippling. Once loads are extracted from the FEA output, Hypersizer performs many different panel buckling predictions. Depending on the appropriate boundary condition, different results are computed. Of particular interest in ship hull design is a buckling failure called stiffener tripping. Pictured are typical inverted T-stiffened panels buckling in either of two modes. For other unsymmetric panel shapes, a possible third mode is flexural torsional buckling, which is a combined interaction of the first two. Hypersizer includes all of these. All local failure buckling modes are also analyzed, such as plate buckling and crippling. Crippling occurs after the plate goes into local instability. Stresses concentrate into the remaining stable cross-section of the stiffener shape until the entire panel crushes. A typical FEM of the hull has only a few elements representing each individual panel bay. Modeling technique 1, the smeared equivalent stiffness approach, is used. In this transparent view, each individual panel bay can be seen spanning the underlying transverse frames. For each of these individual panel bays, panel buckling, stiffener tripping, and plate local buckling analyses are performed to all load cases. Hypersizer accomplishes this by first quantifying the length and width of the panel bay spans. During FEM import, these distances are calculated and displayed on the FEM as red markers.